Welcome back from the Easter holiday weekend. Hope you all enjoyed it. We just have a couple weeks to go, and I have up here the class schedule for the next couple weeks. You can see this week we are going to be covering balanced trees. We're also going to finish up one of the functions from binary search trees that you're going to be doing in the current lab, but which I did not get to last week, which is making a balance tree. So we'll do that first. Then next week we're going to talk about algorithm analysis. So we've already spent a lecture talking about big O notation and how we use that to characterize the running time of algorithms so we can compare them. But we have not talked about how we find the running times of those algorithms, that function t of n. So thus far, you've always been given t of n. So next Tuesday, we'll go over how you count instructions in order to come up with that t of n function. And finally, on next Thursday, we're going to have a review for the final. Originally, that was going to be a third midterm, but I decided it was too soon and too much work right there at the end of the semester because you have a lab due right then. Also, the results on midterm 2 were a bit lower than I'd hoped for. So I'd like to be able to go over in that review session midterm 2. I'm going to review midterm 2 in that review session. And some of the questions from the final will be on from midterm 2. So basically the final will cover everything again from midterm 1 and will include trees as well as what we covered between midterm 1 and midterm 2. You should expect on that final some questions about recursion and questions about which data structure you should use given a certain scenario. And obviously there'll be questions about trees on that final too. So it'll be a bit more heavily oriented toward trees because we have about a month's worth of material since the last midterm, but it's still going to be some problems that cover the material that midterm 2 covered. So again, I'll be going over midterm 2 next a week from Thursday, going over both the coding and the paper version of the exam, and also, if time permits, some review with trees. Now, the final is on May 1st, Friday, May 1st. It's 10:15 a.m. to 12:15 p.m. And the coding portion of the final will be part of the in-class paper exam. So roughly speaking, you'll probably be allocating an hour to an hour 15 minutes to the paper version and then 45 minutes to an hour to the coding version. Okay, so let's get started with today's lecture. And we are going to be talking about starting with binary search trees again. So what we did not cover last time is a function called makeBalanceTree. And Dr. Plank is having you write a copy constructor and an assignment operator for this assignment. If you go up here, you see them. Here's the copy constructor and the assignment operator. And what he wants you to do is have these functions create a balanced tree and return that balanced tree. Those two functions are going to be calling this helper function called makeBalanceTree. You can see it takes a vector of sorted keys, so that will be the sorted keys in the tree, and their corresponding values. So you'll get the sorted keys and the values by calling ordered keys and ordered vals. So these two functions will give you the keys and the vals, but you're being passed those keys and vals So you shouldn't have to do it. That should be something Dr. Planck's code would do. I'm sorry, that's not true. Actually, you're going to have to call these two functions. You'll be calling these two functions from the copy constructor and the assignment operator, and then with the vectors you get back, you will be passing them into make balance tree. And then you'll be passing in the first index to start with where you'll be balancing the tree, and then the number of nodes that you need to balance. So I'm going to go through that. So let's just have a look at an example. Okay, so let's say that we have a tree, and let's say it's something like this. Okay, and let's say that we call the either the operator assignment or the copy constructor. So what we want to do is make a balanced tree out of this. So what we're going to do is start with the keys in sorted order. So that would be 5, then 10, then 20, 22, 25, 50, 100, and 200. And these are the indices associated with them. So what we're going to do to make a balanced tree is going to look a little like binary search. We're going to start with the middle index. And in this case, there's two possible middle indexes, either 3 or 4. Dr. Planck's lab specifies that in this case, you take the higher of the two indices. So you would take 4, and you're going to make that the root. But before you do that, what you're going to do is you're going to recursively call make balanced tree on the lower or left half of the array and create a left subtree. And then you're going to call it on the right half and create a right subtree. And then you're going to create a node with 25 and make it point to the two subtrees that return. So essentially what you're doing is you're going to end up with 25 being the new root, and it's going to have a left and a right subtree. That left subtree will correspond to the values in this part of the array, and the right subtree will correspond to the values in that part of the array. So what you're going to have to do is recursively call the function, the make balanced tree function, with each half of the array. So let's go ahead and kind of trace that out. So what's going to happen is on this half, the call is going to be to make balanced tree. So I'm going to abbreviate make balanced tree as MBT for make balanced tree. And right now, I'm going to just omit for the time being the keys and the value and just focus on the index value you're starting at and the number of indices. So here you are starting at index 0. There's 1, 2, 3, 4 elements you're going to be creating a tree from, making a balanced tree. Well, this is a recursive call, so again what you're going to do is choose the middle element. Well, the middle element here is 20. Okay, again, there's two choices, 1 or 2. You're going to take the higher index, And you're going to, again, want to sort or create a balanced tree with the left subtree on the left half and a right subtree with the right half. So we're going to call make balanced tree, and we're going to call it with index 0, and you can see 2 elements. Okay? Now, make balanced tree, so what it's getting is effectively an array that has 5 and 10. So 0 and 1. And again, there's 2 possibilities because it's even, so we're going to use index 1. So it means we're dividing it so that the left half consists of just this one element. So it's going to be 0 and 1. And the right half is empty because there's nothing to the right of 10. So the second call, recursive call, is going to be to 2, 0. Now these here are both base cases. Okay? If you have a tree with 1 index, like you do here, you return a leaf. So 1 element, you return a leaf. Create a node and return it. The second one is the 0 element case. So this means you want to return an empty tree. And the way we do that is we do not return null. Instead, we return the sentinel node because that is what we want the parent node to point to when it has an empty subtree. We want it pointing to the sentinel node. So in the 0 element case, we're going to return the empty tree. Okay, so that's going to give us a tree that essentially looks like, we go up here, it would look like 10 and 5. Okay, so now we come back up here to this function, and we make our second recursive call. So again, the index was 2, so we're starting here at 3, and we are doing 1 node. Okay, so that's going to return a leaf. This is a base case. And as you can see, that's 22. So it's going to return 22. And 20, which is our middle right here, will be the root of that. So now we come back up to the beginning with 25, and it's going to end up calling make balanced tree with, starting at index 5, and it's going to be 3 elements, 1, 2, 3. So 3 elements. Okay, so you can see that here we have an odd number, so it's easier. The middle index is 6. And the left consists just of the element 50, right consists just of the element 200. So there's going to again be 2 recursive calls, one with starting at index 5 with 1 element, and that's going to return a leaf because that's a base case, and one starting at, we have to write small, 7, and again 1 element, so again it's returning a leaf. So this one returns 50, this one returns a node with 200, and this one's going to return 100, pointing to 50 and 200, which are the 2 nodes returned by the respective calls. Finally, we're back here, and we now have 2 subtrees right there, and we will link them with 25. And you will see that we have a nice balanced tree here. Okay? So this is right here, our balance tree. And we created it from this tree, this tree right here. Okay, so that is one example of make balance tree. Again, it's being called from the assignment operator and from the copy constructor. And what it's using is a post order traversal. Why is that? Well, it's that way because it's calling make balance tree on its left and right subtrees. Then, with the return result, it is doing some processing, which is to make a node and then link that the left and right children that were returned by the two recursive calls in to the left and right children. Let's take a look at Dr. Planck's example. So in his example, he is calling make balance tree on a tree with 7 nodes. And he's assuming that then the index starts at 0. So the index always starts at 0 when you're creating the root of the tree. And 7 will be all of the nodes that are in keys. After that, you're going to be dividing those things in 2. So here, what he's saying, again, you don't have to know, in fact, what the values are. I just gave you a concrete example. But here, what he's doing is, you can see that the middle is going to be location 3. So 0, 1, 2, 3, 4, 5, 6, 7. The middle is 3. So you're going to end up sorting with 0 and 3. And on the right hand, so let's actually go and look at a second example using make balance trees 0 and 7. So he is calling make balance tree with 0 and 7. So the middle element is 3 here. The middle index is equal to 3, which means he's again making a call to create the left tree, and that will start at index 0. So if we're just again looking at a vector, 0, 1, 2, 3, 4, 5, 6. So this was the middle element. So we're creating balance trees. This will be the left subtree right here. The right subtree will be here. So we start at index 0. There's 1, 2, 3 elements. And on the right one, we're starting at index 4, and there's also 3 elements. So these are 2 separate calls that you will make, each with 3. Then you can see with make balance tree, with 0 and 3 elements, 1 is the middle index. So we'll end up calling make balance tree with just 1 element. And over here is also 1 element, starting at index 2. And both of these are base cases because they have only 1 element, so you can immediately return. And the same thing will be true over here with 4, 5, and 6. 5 will be the middle, so it will call the make balance tree starting at 4, and there will be 1 element, this one right here. And that's a base case. And then over here, there's also 1 element. So that's what the call tree, we call this often a call tree to show what the sequence of calls are. Now, in fact, the way it actually plays out in practice, if you were going to look at the recursive calls, what would happen is, let's say the copy constructor called make balance tree 07. Make balance tree 07 will actually call make balance tree 03 and put it on the stack. Then make balance tree 03 will call make balance tree 01. And at this point, that's a base case, so this one returns and it will be popped off of the stack. Now is when we make the call to make balance tree 21. So now make balance tree 21 gets called and it also returns a node and is popped off of the stack. And at this point, make balance tree 03 is able to make its balance tree, whatever that might be, that consists of the element at index 1, and it points to the index elements at index 1 and index 0 and index 3. So now make balance tree 03 has made its two calls, so it returns. And what gets pushed onto the stack now is a call. We're back up here in make balance tree 07. So it calls make balance tree 43. Okay, the first thing it does is call make balance tree 41. Now, make balance tree 41 is a base case, so it's going to return its node and be popped off of the stack. Then we are back here at make balance tree 43. It's going to call make balance tree 61. It returns a node because it's the base case. Now at this point, make balance tree 43 can make a tree consisting of the value at index 5 is the root, pointing to the subtree returned by make balance tree 41, and pointing this right subtree pointing to the subtree returned by make balance tree 61. We now return make balance tree 43, and we're back up here at make balance tree 07. Now it has the subtree that was returned by this function call. That's the left subtree. And it has the subtree returned by the call to make balance tree 43. That will be the right subtree. It creates a new node with the value at index 3. Then it makes the left subtree, or the left child point to the left subtree, the right child point to the right subtree, and it returns. Okay, and now the copy constructor is essentially done. So again, we call this whole thing a call tree because it shows the sequence of calls, shows the sequence of recursive calls. Okay? So again, just to recap, what make balance tree is being called from is the copy and assignment operator. So both of them are balancing the tree, and in fact, just an important note you can see here, when the tree has an even number of elements, there are two potential middle elements, so the code chooses the higher of the two elements. And as I said, the copy constructor and the assignment operator both return trees that are balanced. And again, the first thing that will happen when these assignment or copy constructors is called is that let's find there we go. There we go. So what they'll do is call ordered keys and ordered vowels to get vectors with the ordered keys and ordered vowels. Then they'll call this make balanced tree helper function to create a new balanced search tree. Remember, it will have a sentinel node, and the make balanced tree will do the post order traversal that I just illustrated to create a balanced tree. So this would be good to remember for the lab because you are going to be doing make balanced tree. So a few things about make balanced tree to remember. Okay, so the middle key is greater or higher index, greater index when two indices are possible. Okay, it's a post-order traversal. And there are two base cases. Okay, one index. Okay, return a leaf. Or B, num indices equals 0. And we return a sentinel node. Okay, which is an empty tree. So questions about make balanced tree. You're going to call it from both the assignment operator and from the copy constructor. Okay. Holland, you have a question. Go ahead.
The parameters are keys, vowels, and indices.
Four parameters: keys, vowels, the starting index, and the number of indices that you're going to be using.
And is there a recursive function?
It is a recursive function. So that's what kind of we were showing here with this kind of tree-like diagram. I was showing you the recursive calls that were being made. Okay, and over here in Dr. Planck's, he's doing the same thing. He's showing how make balanced tree is making two recursive calls to make balanced tree. So yes, it's making recursive, it's a recursive function, it's making recursive calls. Does that answer the question, or?
I'm just a little confused how it went from 0, 3 to 4, 3.
Okay, so it did not go from 0, 3 to 4, 3. These were two separate calls. So you started with a call to make balanced tree keys vowels 0, 7. Okay?
Okay.
And it's going to take the middle key, which is at index 3. If you draw a vector with 7 elements, you'll see that the middle key is index 3. So then he's going to make two recursive calls. He's going to make a recursive call to make balanced tree, and he's going to create a left subtree out of the keys at indices 0, 1, and 2. So starting index 0 and 3 indices. Then he's going to make a second recursive call that creates the right subtree. And that right subtree is going to start with the keys at index 4 and is going to consist of indices 4, 5, and 6 because there's also going to be 3 keys in the right subtree. So we're not going, so make balanced tree, this call right here is making two separate recursive calls. One to create the left subtree, one to make the right subtree.
Oh, okay.
Okay? So again, that's what I was trying to get at here with the notebook, is that make balanced tree makes two calls. So that's why I had a left one and a right one, because it makes the first a call here, it comes back eventually, and it makes a call there.
Okay, thank you.
You're welcome. Other questions? Okay. In that case, we're going to move on to balanced binary search trees. So the problem with binary search trees is if things are sorted or in a bad order, presented in bad order. Let's say that they're presented in sorted order, and we create a binary search tree, it's just going to be a long line, and it's going to be very unbalanced. That's part of the reason why Dr. Planck has you make a balanced tree anytime you use the copy constructor or the assignment operator. But unfortunately, rebalancing like Dr. Planck's doing it, you have to look at the entire tree, and that takes order and time, and that's no good. But this linear list that we have here is no good either. It means that in the worst case, we have order n for find, insert, and delete, which is not what we want. What we want is to always have a balanced tree, because a balanced tree is one that always has half. A balanced tree has roughly half the nodes in each subtree. And if you do that, if you have roughly half the nodes in each subtree, then you're going to end up with order log n, find, insert, and delete, because there'll be at most the height. The reason is the height of a balanced tree height of a balanced tree is log n. And you look at one element at each level in a tree when you're doing find, insert, and delete. So the issue is that not all trees that have half the nodes in each half are balanced. So I could have a tree that looks like this, and half the nodes are in each subtree, but you can see that it's plainly not balanced. Okay? In fact, the length of each chain is n divided by 2, which isn't any better than n. So we need something a little bit better, and the requirement is that each node, or each interior node, in a balanced tree is the root of a balanced tree. So this tree right here would not qualify as a balanced tree because this node is not the root of a balanced tree. So while its parent has roughly an equal number of nodes in each subtree, this node right here does not. It has 2 nodes in the left subtree versus 0 nodes in the right subtree, and the same is true of this one. So a balanced tree must be one in which each interior node is also the root of a balanced tree. But it turns out to be too restrictive to force the 2 subtrees to have an equal number of nodes. So it's too restrictive to have each subtree have exactly the same number of nodes. So we say roughly instead. Remember back here I said that a balanced tree has roughly half the nodes in each subtree. So AVL trees are an example of a balanced tree. So the AVL tree says, okay, we are going to require that each interior node, or the height of the two subtrees at each interior node differs by at most 1. Okay? So the height of the subtrees at each interior node differs by at most 1. And that is going to give us a roughly balanced subtree. So let's just look at a few of Dr. Planck's AVL trees. So here are all examples of AVL trees. So the single node is an AVL tree. A node with a single child is an AVL tree. So is a node with 2. And in each case, we can kind of verify that by looking at the number of, or the height of each node. So let's look at this most complicated case because it's probably the most interesting. So let's just quickly sketch that one out that he has drawn. So he has Eunice here, and Eunice goes to Binky and Fred. And we have that Binky goes to Baby Daisy and Daisy. I'm just going to abbreviate it as Baby Daisy and Daisy. Daisy goes to Callista. And Fred goes to Luther. So the way we get heights is bottom up. Okay, so we start at Callista, and depending on whether you're using the book's definition of height or Dr. Planck's, it's either 0 or 1. So I'm going to go with 0 here. So all leaves have 0 height. That makes Daisy's height 1. And as you can see, the difference between Baby Daisy's height and Daisy's height is 1. So the difference is 1, so we're good. And the height of Binky is 2. Hey, Fred's height is 1 because the height of its left subtree is, we say, minus 1. So its height is 1. We can see that these two differ by no more than 1. And therefore, every subtree, the height difference between the heights is no more than 1. By the way, the height of Fred is 3. Okay. Now, let's look at another one. Let's say we had just Eunice Daisy, and baby Daisy. This is not an AVL tree. So its height of baby Daisy is 0. The height of the right subtree is empty, it's -1. So the height of Daisy is fine, or Daisy is an AVL tree. But now the height of Eunice is 2. But if we look at Eunice's right subtree, it's empty, it's -1. Daisy is 1. This is a difference of 2. Okay, so the problem is Eunice, the tree rooted at Eunice, is not an AVL tree because the two nodes, the two subtrees, differ by more than a height of 1. Now it turns out that the way we can rebalance such a tree is with a rotation. So we can rotate about Daisy, dropping Eunice down and creating a tree that looks like this. So we call that a rotation, and when we're done with the rotation, these two heights are 0. So we have a balanced tree because those two heights don't differ by anything anymore. So we call what we did here a rotation. Okay, it's a rotation about Daisy. And that's going to be the fundamental operation. So we're going to use rotations. Okay, so AVL trees are going to use rotations to rebalance a tree. Okay, so an AVL tree, to be clear, an AVL tree is a balanced search tree. Okay, it is a BST tree. It's just a specific restricted kind of balanced search tree. Okay, so it's a subset. AVL trees are a proper subset of balanced search trees. And what we're going to do with, so find is just like find is identical to a BSTreeFind. Okay, insert is going to start by insert just like in a binary search tree, but then rebalance if necessary. And we'll talk about delete on Thursday, so we won't worry about delete today. So what we're going to do with an insert is we're going to rebalance the tree. And we're going to use rotations to do it. So both the book and Dr. Plank give some examples of rotations. So back here, here's some examples that Dr. Plank gave of rotation. So first of all, if we rotate Binky about Fred, Binky becomes Fred's left subchild. We can do the same thing. We can rotate Fred about Binky, and that's why Dr. Plank has drawn this arrow. If we rotate about Binky, we end up with this subtree. Here, we're going to rotate about Waluigi. We're going to rotate Luther down, and you can see that when we rotate Luther down, it becomes a left child of Waluigi. We can do the same thing. We can rotate about Luther, and you can see Waluigi becomes a right child, creating that tree. Okay, so our rotations seem to generally be reducing the height of the tree by 1, which is what we want. It's making it more balanced. Okay, now we're going to do a more complicated example. We're going to rotate about Binky. Before we do that, I'm going to come back up here to look at the more general case. So the more general case, we're rotating about this node D, and the parent becomes the left child of D in this case. Now when B becomes the left child of D, something has to happen to B's left subchild or subtree, which is A. Okay, so what's going to happen is B is going to keep A's left subtree. The problem is D's left subtree, which is C. When B becomes D's left subtree, C right here is going to become an orphan. Okay, we can see C can't be the left subtree of D anymore. So someone has to pick up C. The person who picks up C is B. B adopts C. And you might ask, okay, why? Well, notice over here, as B becomes a left subtree of D, B's right subtree opens up. It becomes free because D is no longer B's right subtree. So B is free to adopt C. Not only that, we know that all the keys in A are less than B. We also know that because B is less than D, all the keys in A are also less than D. So it's okay here that A is a grandchild on the left side of D. What we also know is that all the keys in C are less than D, but we also know that because D is a right child of B and C is in B's right subtree, we know that all the nodes in C are greater than B. So it's okay that C becomes a right subtree of B. Okay, and everything else is unchanged. Notice A remains a subtree of B. E remains a subtree of D. So C moved over to B, and B became a left child of D. Now we can do the same thing over here. We could be rotating about B. In that case, D becomes a right subtree of B. So over here, D has become a right subtree of B. In this case, it is D doing the adopting of C. Okay, because it is no longer going to have a left subtree as it becomes a right child of B. And you can see that all the keys that are in C are definitely less than D. They're also greater than B. So it is fine for C to become a left subtree of C. Okay, so that is what a rotation does. And if we come down here to look at an example where we're going to rotate about, down here, we're going to rotate about Binky. So what's going to happen is Eunice is going to become Binky's right child. Eunice is going to come down. You can see Eunice is now Binky's right child. You can see that Binky kept her left subtree, which is baby Daisy. You can see Eunice keeps his right subtree, that's rooted at Fred. You can see that Eunice became a right subtree of Binky. And you can see that Eunice has adopted Binky's right subtree consisting of Daisy and Callista. It is now Eunice's left subtree. Okay, and as another example, down here we have a rotation about Daisy. So Binky is going to become Daisy's left child. So here Binky has become Daisy's left child. And we have that Binky needs to inherit or take on Callista's orphan. I'm sorry, Callista's an orphan. So Callista becomes a right child of Binky. So do we have any questions thus far about rotations? Any questions about rotations? Okay, looks like we're good. So what I'm going to do is quickly have you do an exercise. I know you did a couple with the homework or the pre-class exercise, but I'm also going to have you do a rotate about Nels. I want you to take a moment and figure out how to do a rotate about Nels. And this is important because I guarantee you on the final there will be a question like this. So just take about a minute and figure out how you'd rotate about Nels. Okay, let's see. Taylor Rogers, are you there? Can I get you to take a stab at this?
I'm still working.
Okay, still working.
It, but I have like the beginning.
Okay, tell me what your beginning is.
I have nails at the top.
Very good.
The root.
Yep, you're right.
And then I have the left subtree from that is Laura.
Very good.
And Laura's left child is Brad.
Very good. So Laura still has the same left subtree. That's excellent.
Yes, but then the right subtree of Laura, I have John. I don't know if I was supposed to change that or not, though.
No. So Laura's left subtree should be completely unchanged.
Okay.
It is Nels's. Take a look at Nels's left subtree.
So Maria would be the right subtree of Laura?
Very good, because what's happening is Laura has an availability for her right subtree because she's becoming a left subtree of Nels. So she no longer has a right subtree. And conveniently, Nels has to relinquish Maria because he can't have two left subtrees. So he relinquishes Maria, and Maria becomes Laura's right subtree. And if you'll notice, so here's the final solution. So Nels is at the root, as you said, Tracy. I'm sorry, Taylor. Still early for me. And Laura still has Brad's entire, so notice Brad's subtree is not changed, but Laura has taken Nels's left subtree, which is Maria, and Nels has held on to his right subtree, which is Sarah and Sandra. And notice the result is still a binary search tree. Laura is less than Nels, and Maria is less than Nels but greater than Laura. So everything is good. Okay, so make sure you understand how to do rotations like this because it will be on the final. Now, the book went through how to do a rotation, so that's what I'm going to do. You're going to have to do that in lab, your final lab. So let's take a look now at the book. And let's go to next section. So first of all, the book is keeping a balance factor, which if you want to do, you can keep a balance factor, but it's really just an extra piece of information that you're keeping. You could just as easily only store the heights of the two nodes, but what the book is doing is it's saying, okay, the left subtree has a balance factor that differs by 2 here. Actually, it's height. It still has a height. So it's saying here's the height is 1 of B, and the height of the right subtree is -1. The height of these two trees is 0, so it's saying the difference in the balance factor is 2. Okay? So whether you keep the balance factor or not, I don't care. It's simply the height of the left subtree minus the height of the right subtree. I think it's an extra piece of information. I don't like to deal with it, but the book does. Okay, so we're going to look at some code. And the book has 4 pieces of code. One is code to update the height. And so we're going to assume that we're calling AVLTree update height. So having the height of a node is very important because remember in an AVLTree, we need to look at the heights of the 2 trees. So when we do a rotation, okay, let's do a very simple rotation. When we do a rotation, say one like this, one thing we're going to have to do is recompute the heights because the height of this one is 0, the height of this one is 1, and the height of this one is 2. When we rotate, this case about 5, making it 5, 10, and 3, we're going to have to recompute these heights. This will be 0. You can see that 10 is 0, and the height of 5 is 1. You can see that the height of 10 has gone from 2 to 0. So one thing we're going to have to do is recompute heights. And we don't want to do it completely from scratch. We just are going to want to recompute heights along the path of the rotation. So looking at this update height of a node, we initially set the left height to be -1 because the height of an empty tree is -1. Then if the left node is not null, remember you're going to have to modify this algorithm for your final lab because we don't use null as an empty subtree. We use a sentinel node as a left subtree when the tree is empty. So you can't just copy this code from the book. You're going to have to do some intelligent modification of it. But if we do have a left subtree, then our height becomes, the left height is the height of the left subtree. We do the same thing for the right subtree. We initially set the right height to be -1. But if the right subtree is not null, meaning it has a right subtree, we set our right height to be the height of that right subtree. And finally, we set our height to be the maximum of the left height and the right height plus 1, because the height of a node is exactly this definition right here. Now notice we did not make a recursive call to the left and right subtrees. I see a lot of labs where students make a recursive call to the left and the right subtrees. That is bad because that goes all the way to the bottom of the left and right subtrees. It looks at all of the nodes in the left subtree and all of the nodes in the right subtree. You don't want to do that. You just want to look at the height of the left subtree and the right subtree. You're assuming they're already up to date. Okay? So it's not a recursive call here. We're just looking at the height of the right subtree and adding 1 if need be. Or not adding 1, we're setting the right height to it. And then down here, we're taking the maximum of the 2 and adding 1. Okay? The next thing we need to do when we do a rotation is we're going to have to set a child. Okay, so when we do a rotation, we look over here, we're going to be setting a new child. So here we are setting, well, actually, let's take a look at the code again. So we are setting a node to be a child of something. So for example, we are going to take a parent, a which child, and a child. So coming back here, let's say that we want to make 10 be a right child of 5. So 5 is going to be the new parent. The child is going to be 10. And which child is going to be right? Because we are making 10 be a right child of 5 down here. So, trying to see if I can't, pull this over a little bit. So what we're doing is we are saying if we're checking to see whether we're making it a left child or a right child. Here, we are making 10 be a right child, so we're going to set the parent's right to be equal to child. And then, the child is not null, we need to update its parent pointer. So we need to make 10's parent pointer point to 5. So that's what this code is doing, is it's making the child's parent point to parent. And then when it's done, we have to make sure we update the height of the parent. So the parent's height, you can see, was, in this case, 1 before. It's still going to be 1, but we need to make sure that we update the height. We're assuming here that 10's height has already been updated from 0 to 2, and we'll see that on Thursday when we look at the code for doing rotation. So that is it. That's just the code for making a child of the parent. And again, you're going to have to do some modification to this code because, we are not using null for the parent. We're using the sentinel node for the parent. So we're going to just have to be a little bit careful in the lab when we're checking for parents. Okay, now rotation also requires that we replace a child. Okay, so we are going to, in a rotation, we're going to be replacing the current child with the new child. So what we're going to need to do is a couple things in a rotate. So coming back to our example, I'm going to, for a moment, erase this so we can see more of it. So I'm going to put the over here. I'm going to move this notebook if I can, just a little bit over. Nope. No, can't. Okay. So we're going to be 10, 5, and I think this was 0, and it's going to be 5, 10, 0 like that. Okay, so in this case, the parent is going to be 5. Okay, and let's just actually, I'm going to make 7 be a right child here so you can see what's going to happen. 10 is going to end up getting 7. Okay, so this is parent, this is going to be child, new child, and 7 is going to be current. So what we're going to do is, first of all, ask if parent left is equal to current child, and the answer is no. Okay, the current child is parent's right. So we're going to come down here and we are going to set the AVL tree set child to parent right new child. So what we're going to do is the new child right here, new child is going to be the right child. Okay, so we're calling parent right and inserting new child as the right child. Okay, so all we're doing is here replacing parent's current child with new child. So at the end of it, 10 is going to be the new child of 5. Now very quickly, I know that I'm pretty much out of time, but we're just going to look at this rotation algorithm. So this is where I want to rotate about 5. So 10 becomes the right child, 7 becomes the left child. So what I do in this case is I have a parent for 10. Maybe that parent, we'll make it a right parent, is 30. So here we have the parent is 30. In fact, you know what? I'm not going to do that. I'm out of time. So what we're going to do is pick this up on Thursday, and I'll go start on Thursday with this right rotation algorithm. And once we've gone through this right rotation algorithm on Thursday, then we're going to move on into doing insertion and deletion, show you how we apply these rotations to get to do insertions and deletions in an AVL tree. So I'm going to leave you with that. I will say you probably, to understand this, are going to have to draw some diagrams. If you just try to slap down code, it's not going to work. You're definitely going to have to draw diagrams and trace through these diagrams. That's what I'm going to try to do with you on Thursday, but you're also going to really have to do it on your own in order to understand it. So I will see you Thursday. Good luck with your balanced tree lab, which you should be working on, and I will see you on Thursday. If you have questions, feel free to stick around. I have office hours today from 3:30 to 4:30. I can also answer questions for a few minutes before I have to go to my next class. So you're all free to go at this point.
Before I forget, actually, is there supposed to be an after-class activity?
Just a moment.